to have as our speaker today Tom Faulkner, who's a big expert in AdS CFT and quantum information theory. He got his PhD in 2009 from MIT and afterwards did postdocs at KITP in Santa Barbara and at the Institute for Advanced Studies at Princeton. He is a faculty member at the University of Illinois at Urbana-Champaign since 2014 and has been awarded the, I guess, Department of Energy Early Career Award and Young Faculty Award. Anyway, it's a pleasure to have you, Tom, and we're looking forward to your talk.
Okay, well, thank you, Stefan. Thanks for the introduction and for the invitation. So I'm going to tell you about some recent work that I did in this paper here. Let me get my highlighter. Which is the subject of which is an algebraic approach to quantum error correction and the AdS CFT correspondence. So I realized that this audience is that topic is pretty far afield, I imagine, from this audience. So as it turns out, when I was writing this talk, I think I'm going to spend most of my time just with an introduction to this topic, and then at the end I'll get on to some of the results in that paper. Yeah, so the talk will be structured as follows. I'll give a background to AdS CFT, some of the elements of the dictionary in AdS CFT. I will, in particular, highlight the recent advance in AdS CFT from, I guess it's now 15 years ago, is this Rutaki-Nagli formula, which really opened up a whole new field within AdS CFT. And in particular, it sort of led to this way of thinking about AdS CFT using quantum error correction. And this is due to this paper here, the classic ADH paper, and it's sort of given rise to some standard picture of quantum error correction in AdS CFT, and I'll summarize that. One important point was made by Harlow, which is this is some self-consistent structure. You can start with an error correcting code and you can derive something that looks like the Rutaki-Nagli formula. So I'll tell you about that. And then the idea of this paper was to try to, a lot of these papers on quantum information in AdS CFT sort of take a Hilbert space approach where they assume, there's tensor factorization and things that are not exactly correct in quantum field theory. So what I'm trying to do is to improve that and put it in the language of some algebraic language, so that then we can talk about the proper structures in quantum field theory, in particular von Neumann algebras and so forth. Some interesting things arose from that this work. In particular, I observed that these error correcting codes naturally give rise to a family of conditional expectations, and this allows one to connect these codes, these error correcting codes, to something called a Longo-Rehren subnet, which is introduced by Longo-Rehren to study superselection sectors in quantum field theory. There's certain issues with this model. It's not perfect. Doesn't capture certain aspects of the AdS CFT correspondence. And there's lots of indications that the way to fix this is to go from what's known as exact quantum error correction, where you don't have any errors, to approximate quantum error correction. And that's work in progress. That's not what I'm going to talk about today, but I think that's sort of where things are going. So let me start with some warnings. These ideas are a little bit, they're still under development, I'd say. I will give you some rigorous results, but the question, of course, is always, is it relevant to physics? Is it relevant to AdS CFT? And that has not been established. What you should think of is what I'm playing around with these structures are sort of toy models at this stage. The goal, of course, is to go beyond that And a really lofty goal is to use this kind of structure to have some kind of axiomatic framework for studying quantum gravity, perhaps quantum gravity in some limit, say in some long distance limit in AdS. And really, it's getting at this question, which is at the heart of AdS CFT, which is how can quantum gravity emerge just from quantum field theory? And so that's still, we have some idea how that works, but it's really, we don't have a complete picture. And I think some kind of axiomatic formulation would be really nice. So yeah. Oh, I should say, yeah, if anyone has any questions, please stop me. If I say something crazy, please stop me.
Actually, just one small question about this last lofty goal. Is this going to be a
Yes.
motivation for the rest of the talk, or will you go into more details about this last point?
No, I will not go into any more details. This is like really way out there. It's very far from that, but yeah. But I will talk about some structures that may or may not play a role in that final axiomatic formulation. So yeah, I mean, it's really a lofty goal. But yes, it is sort of an under a background motivation to all of this. Okay, so let me start just by summarizing AdS CFT. And yeah, so if you don't know any of this, please ask questions. Okay, so AdS CFT is a duality between a class of conformal field theories or quantum field theories, special class of quantum field theories. Yes. Someone's not muted, I guess. Yeah, so it's a duality between a class of CFTs in various dimensions. There's sort of various examples of this AdS CFT duality, so up to including 6 dimensions. It's a duality between this and quantum gravity, and specifically string theory, in one higher dimension. So it's usually thought of as a holographic duality. There is sort of a discrete set of examples, I'd say, but we kind of think of this as a general paradigm for quantum gravity. So, even if the final theory of quantum gravity is not a string theory, it should fit into this framework of AdS CFT. But the examples that we know of come from string theory. So the CFT side of this, so I'll just give you some examples just to be concrete. So there's a specific conformal field theory in 4 dimensions called n=4 super Yang-Mills. It's a SUN gauge theory with matter, fermions and bosons, with sort of the maximum amount of supersymmetry that you can have in 4 dimensions. There's sort of 2 parameters that are important in this game. There's the SUN, the n in SUN, which we're going to take large to make this duality work. And there's the coupling constant, which is the Yang-Mills coupling constant, and you normalize it like this as you take the large n limit. So this is the 't Hooft coupling. So it's an interacting theory. It's often it's studied from many points of view, say path integral formulation. There's also formulation in terms of CFT crossing symmetry, Euclidean quantum field theory, integrability, supersymmetric methods, studying classes of observables in this theory, and numerically, quantum computers even. So this theory has been studied a lot. It has a lot of nice properties that we can sort of say a lot about. But I'm going to study it from a point of view which is not often taken, which is the Hard-Kastler framework. So in the Hard-Kastler framework, we sort of study algebras of local operators in localized regions. So for example, we might take these double cone regions. So O here is some region in space-time. And assign, think about all the operators that act in that region. And that forms an algebra, and lots of people's work has established that we should think of that as a von Neumann algebra, which is of a particular type, so type 3, 1, Right, and so that statement is very important and plays an important role in this structure. There's various things that this framework satisfies related to causality and so forth. So for example, if I have two double cone regions, one is contained inside the other, then the algebra should be a subalgebra. So M1 should be a subalgebra of M2. So that's this isotony statement. I'm going to always work on compact spaces to sort of remove any infrared issues. So what does that mean? So I'll study the theory, for example, this n equals 4 super Yang-Mills theory on S3, on the compact space S3 times R, where R is time. And then in that case, you expect that these von Neumann algebras to be subalgebras of all possible bounded operators on the Hilbert space defined on this S3. Right? So if you quantize the theory, this n equals 4 super Yang-Mills theory on S3, you get some Hilbert space description. And then if you think about the subalgebras, then they sort of describe the local physics. So I'll call this Hilbert space kappa. Throughout I'll assume some causality condition for a fairly strong one, which is called Hague duality, just for simplicity. So that means that if I take the the double cone region associated to the complement, so if I'm working on a sphere, for example, I would take the region. If I had the black region here as my, so this is. What am I drawing here? This is a picture of S3, and I've removed time, and I'm just drawing the time slice, which is this circle here. And if I have some region O, then O prime is just the complement region, and the algebra of operators associated to that complement region should be the commutant of the algebra of operators in the original region, right? So these are all the operators in B of K that commute with M of O, okay? Good. Now, I'll assume some other things at some point, not really, it won't play an important role in this talk. For example, I'll assume this quantum field theory satisfies the split property, which is the statement that if I have two of these double cone regions, for example, O1 is contained in O2, then there should be a von Neumann algebra that splits, that lives in between the two. So MO1 is contained in MO2, but there should be some von Neumann algebra N, which is of type 1. So type 1, are generally algebras, von Neumann algebras associated to for example, bounded operators on a Hilbert space are always type 1 algebras, and they're nice. They have a trace, and we can do nice things with them. They're easier to work with than the type 3 von Neumann algebras. And this is convenient for various reasons. I've given talks before to sort of the algebraic quantum field theory community where this assumption, I think, is not totally obvious. But I think it's completely reasonable for this particular theory that I'm studying, for example, n equals 4 super Yang-Mills, because the thermodynamics of the theory is well behaved, and there's a general connection between well-behaved thermodynamics, as in, the partition function is finite at any finite temperature, and there's this link between that and the split property. In this talk, I'm going to draw pictures where I ignore the fact that I'm looking at these double cone regions, and I'm just going to draw the time slice. So that's pretty standard in my field, but it should be easy to translate between the two pictures. It just makes life a little bit easier to draw pictures. So for example, and the other thing I'm going to do is instead of, I'm going to think about a 2D example instead of 4 dimensions. Of course, there are examples of AdS CFT in 2 dimensions. But just to draw pictures, I'll draw pictures of a theory living on S1 across R. And so here's S1. And or take subregions of S1. These double cone regions are just these diamonds. And then I'm going to drop time and just draw the picture of the S1 here, and then the subregions of that time slice. So I'm going to assume that the subregions live on that time slice. And then to translate between the two, I just take this double cone region OA to be the domain of dependence of this space-like region A here. And similarly for OB. OA, OB. And then associated to these are these von Neumann algebras, MA and MB. I will also sometimes study, at one point I'll mention in this talk, algebra of operators for disjoint intervals, where we have two intervals and we take the union of them. There's some, I assume that there's some von Neumann algebra associated to that, which I'll call MAB. Okay. Okay, so that was the CFT side of things. That's the structure that I'm imagining on the CFT side of AdS CFT. But there's a duality, so there's a duality between quantum gravity. And so on the quantum gravity side, things are even less precise, as you'll see. So it's a string, you should think of it as some string theory in a space-time that's asymptotic to AdS d+1. I will study it. I'll imagine it lives in some weakly coupled limit. So what does that mean? Well, AdS has a natural length scale associated to it, the curvature radius, LADS. And I'm going to assume the other natural length scales in this quantum gravity, the Planck length over the AdS scale and the string length over the AdS scale are much smaller than 1. So for example, this means that G Newton's constant in units of in AdS units is small. Right, and so it's sort of a weakly coupled gravity limit, and so I can study it in principle as some kind of effective field theory, which you can think of as, say, quantum field theory in curved spacetime, where you allow the quantum field theory to back react on gravity, and you also include the quantization of the graviton. Of course, we know there's all sorts of issues in the UV at very short distance scales, but we should be able to control that at long distance scales using renormalization and effective field theory. And that's the sort of theory that I'm imagining lives in the AdS side of the duality. In principle, this is fine. Of course, in practice, we know that quantum gravity is much more complicated than that. So it's not, it's not just short distance issues in quantum gravity. The UV physics imprints itself on the long distance, and the classic example of this is black hole physics. So if you look at a black hole, there's this intimate relation between the area of the black hole and some entropy quantity. So black hole is some long distance phenomenon, and you get something that looks like an entropy, and there's lots of evidence from various points of view where this entropy is counting UV degrees of freedom. It's of the quantum gravity. Some non-trivial objects like strings or D-branes. And these are the black hole microstates, and somehow the low energy theory knows something about these black hole microstates. So good. Yeah. Okay, so I should also say something a little bit about this asymptotically AdS condition. So what we're doing is we're imagining fixing some boundary conditions at the boundary of AdS. So AdS has a boundary, a conformal boundary that looks like a cylinder. It looks conformal infinity of AdS is this exactly the cylinder that I'm imagining putting the CFT on, SD -1 cross R, or the Einstein static universe. And by imposing certain boundary conditions at this boundary, you can make the sort of the time evolution problem, the Cauchy problem, well defined, the Cauchy evolution well defined. Okay, good. So that's the other side of the dictionary. And so the AdS CFT duality is a relation between these two. In fact, the idea is that it's an exact, should be a relationship between the Hilbert spaces and observables. There should be a way to map between the one and the other. Of course, it's just a conjecture. There's lots of evidence for it. Likely, it will be very hard to prove. But the fact that it's hard to prove actually is what makes it so powerful if you assume it's correct. Okay, so the very difficult problems on one side map to very easy problems on the other. So here are some examples of the elements of the dictionary. So as I said, we were looking in units of AdS at G Newton small, and that turns out to G Newton sort of directly maps to 1 over n, or 1 over n squared, where n is the SUN in the SUN gauge theory. More generally, you should think of n as sort of counting the number of, sort of roughly, counting the number of fields in your quantum field theory. So we're imagining studying the CFT in the large n limit. There's this string length in the AdS side that we took to be small, and that's the limit on the quantum field theory side where we take the large coupling limit. So that's, this non-trivialness. There's a correspondence between states in the Hilbert space that we can sort of understand in various corners of this duality. So for example, the vacuum of the theory on S3 corresponds to the vacuum of the theory in AdS, which is just empty AdS, where the quantum fields in your AdS space-time are in vacuum themselves. There's a map between the symmetries. So for example, the CFT has various conformal symmetries, and these map to these asymptotic killing vectors in the gravitational theory. With these asymptotic killing vectors, you can construct charges, and you can construct them in the quantum theory. For example, the ADM Hamiltonian can be constructed in this way, and that's what you should think of as governing time evolution on the cylinder. Yeah, so this Hamiltonian evolution, and that maps to the Hamiltonian in the CFT on S3. Now, the interesting thing, and partly the reason I'm studying on the theory on this compact space, is that Hamiltonian on S3 for CFT is actually, equivalent to the dilatation generator in the theory. So you should think of this as like radial quantization. So the spectrum of that Hamiltonian is just the spectrum of local operator dimensions, where you think about, local operators, and in a CFT, they have a list of dimensions. So that means that, I can take this CFT and I can, I can study the spectrum of low-lying operators, and that should map under the duality to small perturbations of AdS. So in particular, little gravitational waves in the background of AdS will map to the small, low operator dimensions on the left side. Now, if we go to highly excited states, so states with very large energy or very large conformal dimension, in particular, if the dimension or the energy starts competing with this parameter n squared, then you get a large density of states. There's a lot of states in the window at high energies, and these map to on the AdS side to black holes.
Sorry, do you mind if I just ask one small question before you leave the setting of the Hamiltonian?
Yeah.
Before anybody asks, if I was just thinking mathematically, before I can specify an operator, I should at least know what Hilbert space I'm working on. So is there a specification of going from one Hilbert space to the other on the left and the right-hand side?
Yeah, they're meant to be the same. Yeah. So right. Yes.
So this is presumably, I should think of this as a unitary operator that translates from the left to the right. Correct?
Yeah. So later on, I'll introduce an isometry for reasons that will become clear, hopefully. Okay, so then, we have black hole states, and there's some density of states here. Yeah, and there's some density of states, and in particular, that density of states maps to the entropy of the black hole, which is then the area of the horizon. And this is an example where we sort of have some understanding of the microstates of these of this black hole. So this is a black hole in AdS. Okay, so what I'm interested though in is the quantum information aspects of this dictionary. So to do that, I have to tell you about the Rutakinagi formula. So the idea of the Rutakinagi formula is to sort of consider some subregion. Now we can work in this language of von Neumann algebras, but what happens in high energy literature is they often work in some Hilbert space description, where you take the CFT and you imagine it can be split into tensor factors associated to two different regions, A and A prime. This is not obviously true for in quantum field theory, because the algebras are these type 3 von Neumann algebras, so they can't be thought of as operators on some Hilbert space. The set of all bounded operators on some Hilbert space. So this is some approximation, but you get a lot of mileage from this. So, but the idea is we take the boundary, we split it. Maybe we need some UV cutoff to do that. Then we take our vacuum state, we produce some density matrix, and then we do a partial trace. So all things you can only really do in this type 1 setting. But then you get some entropy by computing this von Neumann entropy, trace root log rho. And this is called the entanglement entropy. So Ryo and Takinagi conjectured a dictionary for this quantity. So that's some calculation that I just described on the CFT side. So what is it in the AdS side? And so they conjectured that what you should do is you should to compute that quantity, it's some number. You should take a minimal surface in AdS, which I'll call MA, and it's the red surface here. That has the property the boundary of the minimal surface is the boundary of the region A on the boundary. So okay, so here's the region A, and the boundary, so there's some homology condition between those two surfaces. And then once you find the minimal such surface, then the conjecture was that the entanglement entropy is computed by the area of that minimal surface divided by 4g Newton. So this is exactly the entropy formula for black holes, but just somehow massively generalized. Okay, so some comments about this conjecture. So firstly, the answer is infinity if you actually calculate it, right? So you can do that procedure and you can calculate it. The reason it's infinity is that the area of that surface is infinite because there's an infinite area near the boundary of AdS. Okay, so you can compute it, you find it's infinite. And actually that makes perfect sense. The assignment of an infinite entanglement entropy is the only naturalist sensible assignment of entanglement entropy to a type 3 one factor. So I think that's sort of a nice check of this conjecture. Of course, it's sort of a little bit, it doesn't tell you anything, but yeah. It's been derived in this sort of regularized setting using other elements in the AdS Cft dictionary that we sort of think we understand. And this sort of magical trick called the replica trick, which I won't go into, but it's a way of studying quantum information using path integrals, and it's sort of less precise. But it allows you to justify this formula. There's various improvements that I won't go into much detail. This is a surface in space-time, so minimal surface doesn't make much sense because you can always minimize it by moving the surface in time. So the actual thing is an extremal surface that was observed by these authors. A lot of information can actually be extracted about the entanglement entropy by putting a little cutoff near the boundary. And that regularization seems to conform with our understanding of entanglement entropy in some regularized sense in quantum field theory. There's actually a systematic way to do this that I've worked on. I'll just mention it very quickly because I already mentioned the split property. Is that if your quantum field theory satisfies the split property, there is a natural entanglement entropy. What you do is you take your region A, and then you split it into two regions. So you have A and B where there's a little gap between A and B. Okay, and that's the setting where we expect the split property to apply. If I take OA, it's contained in the complement region of OB. So then you have these algebras MA, MB prime, and in between is some type 1 von Neumann algebra. And you can, of course, in principle, define the entanglement entropy of these quantities. The von Neumann entropy of the vacuum state, which I'll denote by omega. So for, I'll use this notation throughout. So if I have a vector omega, I can construct a linear functional on the operators just in the usual way. And this is what I think of as the vacuum state. And if I restrict that to this type 1 algebra, I can define an entropy. It's not obvious that it's finite. However, there's some recent results by Longo and Shu that establishes in some theories it's definitely finite. But I have a conjecture with a student that that it's computed by the area of some minimal surface defined using sort of a network of minimal surfaces. Using these regions A and B. Okay, so in that way, in principle, we can systematically study the entanglement entropy. So, okay, that's fine. But here I'm going to focus on a different way to think about this. So instead of focusing on this quantity, this entanglement entropy, I'm going to think about a bulk region called the entanglement wedge. So the entanglement wedge is some region in the bulk defined as follows. So I have my boundary region A, which is a space-like region. And then I have my minimal surface or my extremal surface more generally. Then there's some region RA, which is the homology region between these two surfaces, between A and MA. And associated to that, I can think about the domain of dependence in the bulk theory of that region. And that's what's known as the entanglement wedge, which I'll denote as epsilon A. Okay, let me try to draw a picture. It's a bit hard to draw this picture, but yeah, so here is the space-time picture of that. D of A is this causal diamond on the boundary, or OA, we call it OA as well. And in the bulk, there's this sort of equivalent double cone region associated to that, which is this epsilon A. Okay, so and because these pictures are quite obviously complicated, I'm mostly just going to draw, when I talk about the entanglement wedge, this EA, I'll just draw this picture. And I'll conflate RA with the entanglement wedge. Okay, so the interesting thing, so this talk is really trying to establish an intimate relation between these sort of the bulk region, the entanglement wedge, and the boundary region OA in terms of some operator algebra. So in the bulk, I define some operator algebra associated to EA as the algebra of operators in this region for this effective field theory of gravity. Okay, so this is significant. I totally admit this is significantly less well defined than the quantum field theory object. There's all sorts of issues with defining algebras of operators in quantum gravity. You have to address the operators because they carry energy, so they necessarily gravitate, and so it's complicated. But the idea is that in principle, we should be able to define some algebra associated to that region. Because it's a little bit vague, I would like to have a better definition. And my feeling is that if we understand this problem better, that I'm going to formulate this sort of quantum error correction approach, then actually that will give the answer to the question of what this algebra is. But okay, so I will talk about this algebra and assume that it's well defined. So this relation between this algebra NA and then the boundary algebra MA is understood now to be governed by this quantum error correcting code, which is studied by this ADH. So, an interesting observation is that this relation, we need not talk about the entanglement entropy. So it's not well defined maybe. So actually, probably this is the better way to think about the Rutaki-Nagy formula. It's not about this quantity entanglement entropy. It's about this entanglement wedge. Okay, so to understand this quantum error correction approach, I need to introduce a few more things. So if I go back, okay, I'm going to go back to this entanglement entropy very briefly, because this is sort of what allows you to establish this relation. So I told you that Ryu-Takanagi conjectured this formula in terms of the area of this extremal or minimal surface. Notice that, in some sense, in the expansion that we're thinking about, there's G newtons, it's the denominator here, it's small. So this is a really big term, there's a big entropy. So in principle, there should be corrections to that. And you should think of this as some expansion in G Newton. And the first correction is G Newton to the 0th power. And this is some kind of quantum correction. Think of it as a quantum correction. So I wrote a paper a while back with Aitor Lefkowitz and Juan Moldacena about this, where we sort of showed in the same sort of replicatoric way that the quantum corrections sort of had the following flavor. They did two things. So firstly, perhaps the most interesting thing is that they include an entanglement entropy associated to this bulk region, the entanglement wedge, or associated to this bulk algebra for the particular state that you're interested in. But they also promoted the area term to an operator. So you should think of the area as some operator in the quantum gravity. And in different states, different values. So this sort of area operator takes into account back reaction from excited states. So if your state is some excited state about AdS, it can perturb AdS, and so it can change the area of that minimal surface. And so at least for small excitations, we should be able to understand it in terms of this formula. So continuing along these lines was an important paper by Jaferis, Lefkowitz, Moldacena, Su, which I'll call JLMS, where they now computed a much better behaved quantity, which is this relative entropy. So the relative entropy I will denote as follows. It takes two states, or I'm going to think of them as vectors in the Hilbert space. So psi and omega for some particular algebra MA. This is the boundary relative entropy. And what it does is it compares those two states where the states are restricted to MA. Okay, we take the vector state, the vector in the Hilbert space, we construct the state, and then we restrict to the subalgebra MA, and it compares those two states and it restricted to that region. There's a formula for it in terms of type 1 density matrices. I have some density matrix for one of the states reduced to some region and for the other, and then you just form this combination.
And in general, the restricted states are faithful. What happens to them?
They need not be, although you have to, I mean, you can define them for faithful, non-faithful states. I will mostly assume faithful states. Good. So the important thing about this to understand how this is a comparison of two states is that this quantity vanishes if and only if the states are the same. Okay. And another important thing is that I just gave a definition in terms of density matrices, but there's a general definition for general von Neumann algebras given by Araki, which I won't write down, but you can do it using modular theory. Okay, so that sort of suggests this quantity is a well-defined quantity and perhaps the better thing to study. And so JLMS noted that on computing this quantity, the relative entropy between two states that at least sort of don't involve a huge amount of back reaction compared to each other for some boundary region is equal to the relative entropy of this bulk region that I just defined, plus some small corrections. So it's this relation that really established the strongest connection between these algebras. Okay, and so then, so just keep in mind this JLMS result, which we're going to come back and use, but it's relation between the bulk and the boundary relative entropies. Okay, so now let me get to this quantum error correction approach to all of this. So the idea is the following. So, well, I'm going to give a sort of general introduction to quantum error correction, and then I'll say how it relates to AdS Cft. So the idea is we have some So we have some physical Hilbert space, which will be the CFT Hilbert space, and then there's some code subspace in that physical Hilbert space, and that's we want to encode information in that subspace that's somehow protected from errors. I'm going to think about that as explicitly using some isometry. So I'm going to take some isometric embedding between H and K, which satisfies V dagger V as the unit on H, and VV dagger is some projector, which will be E on this Hilbert space kappa. And so the physical idea is, say in physics, where in some type 1 setting, you have some density matrices on this Hilbert space H. We take, so on the code subspace, H is the code subspace, we take this isometric embedding, we pass that to the physical Hilbert space. That's the encoding map. And then we apply to that a quantum channel. Okay, so T here is a quantum channel. It's a completely positive trace-preserving linear map on states, density matrices. So T is often called the noisy quantum channel. And what we'd like to do is we'd like to correct for that channel. So we'd like to decode the original density matrix from the output of that channel. So the goal is to find another quantum channel, R, which undoes that. So we take R, we apply it, and we get back the original density matrix. So in the algebraic setting, well, firstly, it's natural to think about the density matrix rather than some density matrix as some element of the predual of the algebra of operators, which in this case is B of H. So the predual is just the linear functionals on that algebra with some continuity requirements. And T in that setting is quantum channel is a map on these linear functionals. Yeah. So in this case, the appropriate channel is T is a map from linear functionals on kappa to linear functionals on some von Neumann algebra M. In principle, it could be some subalgebra or something of the original Hilbert space. Now, it's natural to study this from the operator point of view. So this is sort of the point of view where we think of the quantum channels as acting on states. We can also think about the quantum channels acting on von Neumann algebras. And to do that, T, we define the adjoint of the map T in the following way. T of rho is some linear functional on operators M. And I can think of that as rho composed with T dagger acting on M. And so T dagger is this channel between now the von Neumann algebras M and B of K. Operators in the, yeah.
Sorry, just a small question on the states on M. The reason you chose a subalgebra M is because you might not want to recover all your density matrices. You might only want to recover a subset.
That's actually no. I'll do that in a little bit. I'll come to that. Right now, you should think of that as being I'm losing. The quantum channel is losing information. So a natural thing is something where we sort of trace over density matrices, do some partial trace over density matrices, and then we're left with some linear functionals on some smaller algebra. And so that's just the noise. It naturally acts like that. So in terms of the adjoint, we go from some subalgebra to the original bounded operators on the physical Hilbert space. Yeah. So I'll get to your point in a little bit. So quantum channels is so now when I refer to a quantum channel, I refer to a completely positive map on von Neumann algebras. So I'm going to focus on operators rather than on states. And in that case, you can also define a decoding map, which is the dagger of the original decoding map, R dagger. And if you track through definitions, R dagger takes bounded operators on H to this algebra M, such that there's some recovery condition. The adjoint of the recovery condition can be written in terms of the von Neumann algebras and looks like this. And so roughly what you should think of as going on here is that I'm encoding the logical operators. The logical operators are the operators that act on the code subspace. And I'm taking those and I'm mapping them into protected operators in the physical Hilbert space such that the action of the noise does not affect those operators. And so that's what this decoding map says. Okay, so in AdS Cft, T, the original T, will be what's known as an erasure channel, where we sort of trace over the boundary region A prime, so the complement boundary region A prime. So here's our boundary CFT on a circle. We take A prime and we're gonna trace over it. We're gonna throw it away. It's part of the noise. The code subspace in this case should be thought of as this relation between AdS CFT, but where in the bulk, I'm thinking about this effective field theory of quantum gravity, which is sort of necessarily a subspace of the Hilbert space of the full theory. So in principle, this is a complete duality between states on one side and the other side. But in practice, because we're just thinking about effective field theory, some low energy limit, we're actually excluding lots of things. And stringy and D-brane excitations. So there's some natural projection that arises in this language. I'm not giving you a precise version of what this projection is, but there should be one. Okay, and then the recovery map in this language, if I think about the adjoint recovery map, well, it's now mapping from the logical algebras, which are in general bounded operators on this bulk Hilbert space H. So I should have said, yeah, so this is the bulk Hilbert space. It's the gravitational Hilbert space. I'll call it the bulk Hilbert space. And this is the boundary Hilbert space. It's the CFT Hilbert space. So the recovery map takes the logical operators and should map it to the boundary region. Now, it turns out that in this case, we can only protect against errors for logical operators that live in a subalgebra of B of H. So I set up quantum error correcting codes in the more sort of the standard way of setting up a quantum error correcting code. But it turns out that the appropriate quantum error correcting codes for AdS Cft is something called a subsystem code, where you can only protect for a subalgebra of the code subspace. And so, yeah, so that's the actual structure that arises. And then the recovery map is a map from a subalgebra NA to MA. Right? So then that's this relation between these two algebras that we've established, we're trying to establish. Okay, so the picture is the following. In AdS, we have a boundary, we have boundary region, we have some bulk region NA. If we trace over the boundary region A prime, then we're throwing away A prime, but we're also throwing away a bunch of the bulk. And the idea is that we're throwing away a bunch of the bulk theory up to the minimal surface or the extremal surface. So in particular, the idea is we should be able to encode N, it's some operator in this entanglement wedge, in M of A. And this encoding is exactly the problem of bulk reconstruction. So this is a thing that has been studied for a while in AdS Cft. Okay, so all right, and so this map, this R dagger map, I'll call beta from now on. So it's a quantum channel on von Neumann algebras, and it's something that takes the bulk operators to the boundary operators from N to M. Now the non-trivial claim, so I've just made some claims here, but then this is it's a highly non-trivial claim that the entanglement wedge is the thing that encodes the protected operators in this case. It's highly non-trivial, and that can be seen in some examples. So in some simple examples where you sort of think of geometries that are slightly different from AdS, there can be quite a big difference between what's called the causal wedge of some boundary region and the entanglement wedge. So the causal wedge is defined in terms of the future and past of the boundary regions. Basically, it's all the regions in the bulk that are not space-like separated from the boundary region D of A. So there's some causal relation between the causal wedge and the boundary region. Now, the entanglement wedge can be different from that, right? So remember, the entanglement wedge is defined in terms of minimal surfaces. It didn't, or extremal surfaces. It didn't say anything about causality. And there are some times when it can be quite different. So that means that I can encode in the boundary Hilbert space operators, say, in this sort of region between the two. So this is the causal wedge. This is the entanglement wedge. And because they're necessarily space-like separated from the boundary operators, it's not possible to encode them in a simple way, right? So it has to take into account some highly non-local effects in quantum gravity. And that seems to be what's happening. In particular, you should think of those operators, when you encode those operators in the boundary Hilbert space, they're really complicated operators in the n equals 4 super angles. They're highly complicated operators. Another example is if I have two disjoint regions, A and B, the causal wedge is sort of this region here, and the entanglement wedge can sort of connect. Right? So the minimal surface of two boundary regions can sort of have this connection between the two regions like this. And in that case, there's a huge region of operators that are not causally connected to the boundary that can be encoded using this error correction idea. And the final example is something of a hot topic these days, which is exactly this idea, which has led to our understanding of how the black hole information paradox is resolved, or there's some hint of a resolution using this idea of bulk reconstruction. In lieu of time, I'm not going to go into the details of that, but if you want to ask, I can tell you more about that. So the question is, how do we establish the existence of this map, beta? Well, we use JLMS. JLMS told us there's a relation between the relative entropies. I'm going to rewrite that relation a little bit in lieu, with this new knowledge of thinking about the bulk Hilbert space as some code subspace. So I have this isometry that takes psi and omega. Psi and omega are now vectors in the code subspace, and I map them to the boundary using V. Then the relative entropy of M for those two states should be the same as relative entropy of N in the bulk plus some small corrections. So it turns out that with such small error, with such a small shift in the relative entropy for all states, it's possible to prove that there's something, that there is a recovery map. And it goes under the name of the Universal Recovery Map, which was originally established by Junge et al. And it's basically a recovery map that undoes this noise T. This map was originally applied to AdS Cft in a type 1 setting here with Stefan and Brian Swingle and Yishu Wong. We generalized this to general von Neumann algebras, this sort of universal recovery map statement. And part of the motivation for me for doing that was to try to apply that to AdS Cft. But here, actually, I'm going to follow a different approach. It's called the DHW approach. And it sort of looks, instead of at the algebras M and N, we look at the commutants. So we're going to apply the JLMS result of the commutants. It's still true for the commutants. So the relative entropy of M prime should be equal to the relative entropy of N prime. And we're going to consider a special class of two bulk states, psi, such that when they're restricted to the commutant, they're the same. So the linear functionals are restricted to the commutant, they're the same. So in general, that means that the two vectors are related by an isometry in the algebra N.
Yes. Just a small question about the previous point about the universal recovery maps.
Yes.
In general, you first set up the QEC approach where you needed a left inverse map. Isn't this not necessarily the same as a universal recovery map in general? You're referring to like the Pets recovery map in this case? Because that
Correct, yeah.
Because that need
Yeah,
not always be a left inverse. So how are you relating this recovery map to the one you had mentioned about QECs earlier?
There's one extra step that I'm missing that I'm not going into. But basically, you have to construct a channel out of the structure that I've given you that maps the appropriate algebra to the appropriate algebra, and you can do that in a type 1 setting. So there you need a factorized state. If you have a factorized state, you can construct the channel and then you can reverse it. So that's what they did. And it's fine in a type 1 setting. I do not know how to do that in a general setting.
Okay, so in general, the Takisaki's theorem holds, the modular group, the necessary modular group condition holds?
Good. So it's approximate, so no, it doesn't hold. In that case. So what I'm going to come up with is a structure where Takisaki's theorem does, it does hold. But I'm going to assume things are exact. So in some sense, I'll get it out of that. Yeah. So okay. So okay. So yeah, I maybe I misunderstood your question. This map that Junge wrote down is not the PETS map. Something called the twirled PETS map. And you need to do this twirling in the approximates. Maybe that was more related to what you were asking. Yeah, so the PETS map doesn't actually work. You need to do the twirling. Okay. Okay, so I'm going to use a slightly different approach, this DHW approach. So we consider two vectors, psi and omega, with linear functionals agree on n prime. If that's the case, the relative entropy in the bulk for n prime vanishes. That means that the relative entropy on the boundary using JLMS is small. It's actually believed to be much smaller than this. It's believed that in this case, when the states agree, it's actually non-perturbatively small. I'm going to assume that it's exact just to make some progress. But it's actually important, as I'll discuss, hopefully, to fix this. Okay, so then the statement that we're looking at is that if the linear functionals on the commutant in the bulk agree, then the boundary linear functionals on the commutant M prime should also agree once I map these states to the boundary. And so this is called the DHW condition, and it really links these algebras. So this is some condition. There's another condition which is called reconstructable. The reconstructable condition is just this question of finding a boundary operator for a given bulk operator. So if I have an operator in N, then there exists an M that has the right action on the code subspace as N. And so DHW actually showed that these two conditions are equivalent for type 1 von Neumann algebras. And so physically what's happening here is this condition B is telling us that information about N prime encoded in the differences in these states on N, sorry, information about N, which is allowed because they can differ on N, cannot be detected in M prime. So all the information has to go to M, and that means you can recover it. So to understand this structure, I give a well-known theorem. So in the general setting, so this theorem wasn't applied in the original papers, but it's an old theorem going back to at least the 80s and probably the 60s, which tells you the following. So if I take this DHW condition on the linear functionals, then I can turn that into a statement about a quantum channel. So the quantum channel is the global quantum channel is just conjugating by V dagger V. So I take operators in the boundary Hilbert space, I conjugate by V dagger V, and I get an operator in the bulk. If I restrict that to the commutant M prime, that's a quantum channel alpha prime. In general, alpha prime is going to go to operators in the bulk in B of H. If the DHW condition is true, you can prove that alpha prime restricts nicely to the bulk algebra n prime. So it's a quantum channel between m prime and n prime. So that's a condition. It's not, this map does that. And so condition. So these two conditions are sort of somewhat easily related. You can think of one as the Schrödinger picture version of the other, which is the Heisenberg picture. But the non-trivial fact is this is related to this reconstructability condition, which can be stated as follows. There exists this recovery map beta, which takes the bulk algebra to the boundary algebra. It forms a star homomorphism, so it preserves the algebra, and it satisfies the following recovery condition. Okay, so this relation between alpha prime and beta is important. It's sometimes called the dual map. It's a version of this Petz map without the modular conjugation operators. Good. I've stated a version of this theorem that requires a cyclic and separating vector v psi for the boundary algebra M. So there has to be a code, a vector in the code subspace that maps to a vector in the boundary that's cyclic and separating from the boundary algebra M. Okay, and then this beta of n defines a von Neumann subalgebra of M. The recovery condition.
The map alpha prime lands in n prime, or m prime. I forgot n prime. But is it also n prime bimodular? So is it an actual expectation onto n prime?
I'm getting there. It will be with one extra condition. Yeah.
Okay.
Yeah. So if A and B satisfy this DHW condition or one of these conditions, I will say that n is reconstructible from M. And it turns out that this is a rather weak condition, but AdS Cft gives you a much stronger condition. And that's the condition of complementary recovery. So I'm going to say that n is C reconstructible from M if both n is reconstructible from M and n prime is reconstructible from M prime. So then we get, multiple maps. We get alpha, beta, alpha prime, beta prime, right? So applying sort of this theorem twice. And so, here's a picture of that. I'm going very quickly because I know I'm out of time. So you should think of n being C reconstructible for M from M is basically the thing that defines this entanglement wedge. So C reconstructibility is a very strong condition. Reconstructibility is a weaker condition. You can show that any subalgebra of a C reconstructible algebra is reconstructible, and this is an if and only if statement. Okay. Yeah, good. Okay, so the main result, which is just really an observation, was that these structures are consistent with the existence of a conditional expectation. So if n is C reconstructible from M, then there exists a conditional expectation, which you construct using a composition of maps beta and alpha, which takes M to this subalgebra n beta. And it has the property that it preserves the code subspace. Yeah. Okay, so a conditional expectation is a special quantum channel that acts, that takes an algebra to its subalgebra and satisfies this bimodule property. And it's a non-trivial statement. The existence of it is a non-trivial for general von Neumann algebras to certain subalgebras. Okay, so perhaps everyone is, I don't know if everyone's familiar, but I'm running out of time, so yeah, so here are some examples of conditional expectations. Okay, so it's not hard to check this claim, so I'm not going to go into that, yeah, actually, again, because of time. But okay, so the consequences are many. The equality of relative entropy through the code, this JLMS condition follows from a well-known paper of Petz because of the existence of this conditional expectation. There's an inequality between the bulk and boundary modular flow, which I have not talked about, but it's something that plays an important role in AdS Cft. And this is a well-known result due to Takasaki. yeah, so we can rederive the quantum corrected Rutakinagi formula, which was sort of the motivation for this. If I work in a type 1 algebra, you can prove that the entropy of the boundary von Neumann algebra is related to the entropy of the bulk von Neumann algebra, plus a term which lives in the center of the algebra, Ln hat. And the idea is you should think of this as the area operator. Right. So remember, in the quantum RT formula, I had this area operator plus the bulk entropy, and the area operator is something that sort of lives on the surface of the RT surface, Rutakinagi surface, and so in some sense you should think of it as living in the center. Okay, all right. I'm going very quickly. I'm going to skip that. I just want to get to the main punchline, and then I'll finish. Okay, so how far can we push this? If we have multiple boundary algebras, then we get multiple. If we have multiple boundary algebras and their associated bulk algebras, and we assume that they're C reconstructible in this way, then we can prove all sorts of nice things. We can improve something called entanglement wedge nesting, which plays an important role in AdS Cft. And I don't have time. But the important thing is this consistency of the conditional expectation. So if I have two boundary algebras, M1, M2, M1 is contained in M2, I assume that I have two C reconstructible algebras, N1, such that N1 is contained in N2. In fact, that has to be a previous theorem that I didn't go into. Then you can prove using a structure that this conditional expectation restricts nicely. So if I take M2 and I restrict to the subalgebra, it's E1. Okay, and this consistency proves that this structure of exact complementary recovery applied to multiple boundary algebras, say a net of boundary algebras, is the same as the structure of a net of inclusions that was studied by Longo-Rehren. And this is a general mathematical structure behind superselection sectors. Okay, so in that, you have some, say, set of double cone regions, and you have two algebras assigned to those double cone regions, such that one is always a subalgebra of the other one, and there exists a assumed conditional expectation that restricts in this way.
I'm
okay.
sorry, just maybe I missed the point. You can hear me?
Yes, yes.
No, but this conditional expectation, it is normal or?
Yeah, it's yes. It's it's faithful and all. I've assumed the existence of a cyclic and separating state, and so that you can prove it's faithful and things like that.
It's normal.
It's definitely normal. Yeah.
Okay. Thank you.
Mm-hmm. Yeah, all of my maps were normal. Yeah, I assumed continuity. Okay, so this connection was pointed out in this paper, and at least the connection between superselection sectors and AdS Cft was pointed out in this paper. And so my paper was just sort of establishing this connection more rigorously by this DHW condition. Okay, so in this Longo-Rehren subalgebra, Ni is the subalgebra of neutral operators under some global charge, say, and E projects to this neutral sector. So in AdS Cft, you should think of E as projecting to the low energy gravitational degrees of freedom. I do not have a specific proposal for what E is. However, our understanding of quantum information in AdS Cft suggests that some E should exist. There's an important issue with this, which is, yeah, I don't know. Do I have time to explain this? I'm way over time. So someone should let me know whether it's just 1 or 2 slides, but I can also stop now.
Yeah, maybe. I think I'm not sure how long people will be able to stay on. So in particular, for example, I have to leave. So maybe.
Let me finish. So
finish.
Forget this. The basic point is. The basic point is that there are some issues with this. They don't quite work in AdS Cft. And you can always this is not the only issue here, but you can always sort of, all indication points that the problem is this exact recovery condition. So as I said, it's believed in any case the relative entropies have small non-perturbative corrections, but turns out that those corrections can have really significant effects. And so, the goal in the community, the AdS CFT community, right now really working hard to try to understand how to improve this to some approximate error correction. There's all sorts of complicated things that arise in that setting, but I really think that thinking of it from this sort of algebraic point of view, trying to connect to things that algebraic quantum field theory people know very well is quite fruitful. Okay, and so thank you. Stay tuned for this approximate thing. Okay.
All right, thank you, Tom. Sorry for.
No, I'm sorry. I'm sorry. I
just wanted to have a few more minutes for a few questions, if any.
Okay.
So questions are invited. We have already had a few. So maybe while people are making up their mind, in your approach, I mean, are these inclusions finite index, because a lot of the power usually comes from such kind of conditions?
Yeah, that's a good question. I do not know. So I don't know. So the one thing that I can say is that if this analogy is correct, then we should think of the area operator in this Rutakinagi formula as being sort of the central term in this in this sort of inclusion. Then well, it's not clear if the thing. Well, I mean, the expectation value of that area operator should probably be infinite. So I think that likely that implies that the index is actually infinite. So I think that kind of makes sense. So I'm not too familiar with it, but that I guess in rational CFTs you can study this these Longo-Rehren nets, and you can look at some subsectors, and in that case you get a finite index. But in many senses, AdS CFT is thinking about irrational CFTs. So I think that there's something to be said for that. Which maybe it's going to complicate things a lot, but maybe that's also the reason that this is not quite working at this stage.
Okay, thank you. Were there any other questions? You can also type them in the chat.
I have a question.
Sure.
So maybe you said it, but when you started with this quantum error correction setup, you said that basically the bulk theory, this vector field theory for quantum gravity, should be the code subspace, and the the question I am asking is if so you usually in this AdS CFT correspondence you have this dictionary, and I thought that the conjecture at least is that it's somehow exact mapping, but so in this quantum error correction setup, the channel is considered to be noisy. What is the noisiness in this setup then when you use the bulk boundary?
Well, there's two things. So firstly, there's the code subspace, which means that that somehow I'm not studying the complete quantum gravity in the bulk, but that's sort of natural from an effective field theory point of view. You're missing all sorts of UV degrees of freedom. So I should sort of understand that from that point of view. Now, the noisy channel specifically is just this erasure channel, which just means you're restricting to some subalgebra on the boundary. So that that is you're restricting your states to some subalgebra. That is, that's something that I can always do, even in a a completely well-defined theory, in a non-noisy theory. It's just I'm choosing to ignore part of the system.
Yeah, okay. I just didn't get it
Yeah.
the talk.
No, but I
you.
think your question in terms of the isometry is relevant, and there, we think of AdS Cft as being a complete duality, but somehow to understand this quantum information, these root Takanagi formulas, these entanglement wedges, and so forth, requires us to think about a code subspace.
Okay, thank you.
Okay, there are no more questions. Thanks, Tom, again.
I think there's one question by
There is?
Sebastian.
Oh, okay. Then it should be asked. I haven't seen it.
Well, I think he just did not unraise his hand.
Yes.
Someone kept his hand up.
So I have a very tiny question. Conceptually speaking, if you have approximate error correction only, what does that tell you about the physics if you're only approximately recovering information? In this case?
Yeah, I think it's good. I mean, I think this structure will, maybe it won't tell you about the precise duality. It will only tell you some approximate thing about the duality, which is still interesting, I think. So yeah, I mean that's true. It seems necessary. So I think it's just something that we have to live with. But I think there's still things that we can learn even when it's approximate.
All right. I guess it's time to go for tea or whatever is your favorite beverage at this time of the day. I guess in the US it's a little early in the day for a whiskey, but we could have one if we haven't got other meetings coming up. Thanks anyway for joining, and see you next month with
no, not next month. Okay, we have there's no session in May. I think next.
So the next one is in June with
Henrik Weber.
Henrik Weber from Bath on stochastic PDE, I suppose. All right. See you. Bye.
Goodbye. Thank you.
Bye.
Thank you.
Thank you. Goodbye.
Bye.